Welcome everyone to the ESCoE Economic Measurement webinar. I'm Charlotte Min. I am a research associate at ESCoE and will be chairing today's session. Today we will have Dr. Thies Lindenthal to present his work towards accountability in machine learning applications, a system testing approach. Thies is a senior lecturer in real estate finance at the University of Cambridge. His research is dedicated to understanding property values with innovative data sets. These data sets include, for example, house prices and rents with up to 500 years history, as well as high-dimensional big data. Today, he will focus on the latter. This presentation will be around 40 minutes, followed by a Q&A session for about 20 minutes. If you have any questions, please type in the Q&A box at the bottom of the screen at any time. We will take questions after the presentation. Please also note that this webinar will be recorded and the video will be on the ESCoE website. Now, without further ado, I will hand over to Thies. So Thies, if you could start when you're ready. Thank you.
Hello, everybody. My name is Thies Lindenthal. Thanks for having me. I'm very, very excited that you allow me to talk about something that I really like talking about a lot, and that is how we can learn more about the built environment by simply walking down a street. So one part of my research is really all about this phenomenon that you probably know very well as from your explorations of cities, is this great thing of just walking through a city, look at the properties, look at the spaces, look at the street, look at the cars, look at the people, and then really try to understand what is going on in these cities. And that is something that I personally enjoy very much when I come to a new city, but I also enjoy that when I revisit streets and cities that I've seen before. So coming back to exactly the same spaces allows me not only to see new things that I haven't seen before, but also to see how my view on things has changed. So in the meantime, I might have learned new details about the economy of the city or the way how things are built or who's living where, and that will absolutely shape then the way how I can then make sense of what's around me. And in addition to that, what's also usually very, very enjoyable is to do this with friends, to not walk alone, but to see how other people are looking at the city, to understand what their concepts are, and also to see them by reflecting on their concepts, what my concepts are. So what I'm trying to do in a research agenda here is I'm really trying to do exactly that thing, to try to give this experience of walking down a street, give that to computers. So I'm going to talk here about three elements of my research agenda, which are all around this walking down a street theme. So in the first few minutes, I will talk about a paper that has been recently accepted for publication, in which Eric Johnson and I tried to extract information about buildings from street level imageries. So we try to replicate this experience of walking down a street, making sense of what is on the left and right, and then use that information then to understand the economics of cities better. So it's all about extraction of information from, let's say, Google Street View. Then the main part of this talk is really then about trying to understand how good these mechanisms, these tools, these methods really are that we use to automatically extract information from, let's say, Google Street View. So what do these models really pick up when they look at buildings? Is that what we think they pick up? Is that what we hope they pick up? Are they behaving in the way we anticipate them to behave? This is really the core part of this talk here. And I will use a few minutes at the end to talk about a new project we've just started, and that is exploring how what people are really looking at when they're looking at houses. So it's an experimental setup. Right, so let's start with the first one. In this paper, with Eric Johnson, we try to teach computers to see what is on Google Street View. So we try to infer quality or style attributes from about attributes of buildings from street level images. And so generally we just try to use Google Street View, walk down the street and see what kind of buildings are on the left and right. And we, in order to do so, we combine a number of toolboxes that have been developed by other people, but we bring them together in a new and, I think, innovative way that hasn't been done before. So what we do is we first harvest images, mugshots of individual buildings from Google Street View. Sounds easy, is not that complicated if you're in America, but if you have to deal with unruly UK addresses and house shapes, it's quite a challenge. So the first thing we do there is we really try to build tools that allow us to get exactly that front, that facade of an individual building. Then we take these mugshots and send them through a computer vision machine layer model that will then translate the pixels into something called a feature vector, which is a numerical representation of that image. Let's say, think about a vector that has 2048 elements. That's the type of data we're working with. So it's translating pixels to a high dimensional representation. Having then derived these feature vectors for each building, we then can add another layer of machine learning and then, for instance, classify these feature vectors, and by that classify the buildings behind these feature vectors into, for instance, vintages. And once we have done that step, we can then use that explicit information that we've derived from the street level imagery, and we can then use that, for instance, to study price effects of vintage. Each of these steps is not new, has been developed by other people. What we just do is we bring these steps together, and by that we can answer questions that haven't been answered before. So the big advantage of this approach is that it is scalable and it is cheap. So at the moment, we're collecting images of every building in the UK, or at least every building that can be seen by a Google Street View car. And then we try to learn about that housing stock by running a number of the models that I've just described before. So we try to then, for instance, determine the vintage of each of these buildings. And that is what you can see in this map here. That is a map of a subsample of our data where each dot represents a house, and the color represents then the vintage in which that house has been built. The big advantage of this is not only that it's scalable, but it's also complete. So we can get information not only about the houses that are in some database or that have been sold at some point in time or that have been listed at some point in time. No, it's really every building that's on the ground. So that's not just the building that we might be interested in itself, but also its neighbors and the houses that are maybe across the street. So we have this full urban picture of observations, which is, I think, very appealing for urban scholars. So the key finding from that paper, beside just showing how you can build such an pipeline, such an analysis of urban shapes, is the key finding is simply that there is no price premium for new buildings that are built in traditional styles. So if you have the choice and you can either build something new in a modern design or in a somewhat, let's say, fake Victorian design, there will be no direct price effect on that particular building. And also there will be no price effect on buildings that are in the surroundings. So there's no indirect spillover of, let's say, these aesthetics to other property values. So this entire story about the housing crisis in the UK would be over if we just built according to historical designs. We don't find evidence for that at all. But we only look at Cambridge, and Cambridge might be special in that. Right, so I wanted to talk about this paper to give you a bit of a introduction of what these methods are capable of and what kind of questions can be answered, and what kind of questions we have already used these tools for. We looked at the vintage for a start, because that is relatively easy to do. But you could look at other features as well. So for instance, on this image here, you might not really see it very clearly, but there is an electric charger visible. So from that street level image, you could derive that this household has actually made the switch from a traditional car to an electric car. If that is what you're interested in, you can study that. You could also see which houses have solar panels. You could see which houses have been converted their lofts already, their attics. You can see so many different things from the street, and that should really help us to have a richer picture of cities. But that's not really what I want to talk about here. So what I want to talk about today is the next step. And the next step would be then to really see what it really is that these models pick up. So you don't have to care about this if the only thing you're interested in is raw predictive power. So if that's what you're after, then just train your models, increase the sample size, increase the image quality, and tweak the models, and you will have a very, very, very powerful tool at hand. But if you're an economist, and if you want to be able to interpret the values, if you want to be able to communicate what kind of factors are causing a specific outcome, well, then what we really need to have is a better understanding of what is happening inside that black box, what is happening under the hood. And this ability to communicate the outcomes is especially important for, let's say, automatic valuations that go to property taxes. If you, for instance, in countries like the Netherlands or the United States, property tax is calculated on a regular basis automatically. If you then have to explain to the households how much property tax they have to pay, it's not acceptable to say, yeah, my model tells me you have to pay X. You have to also be able to say, my model tells me you have to pay X because of A, B, and C. And so with black box machine learning approach, you can't do that. So the goal then of our research is to, let's say, have a little bit of an understanding of what's going on here, so that we can actually say why a certain outcome is coming out of our systems here. Hopefully, it allows us also to be a little bit stronger in establishing causal inference. As an economist, that's something I'm really, really interested in, to say, okay, A causes B, and for that, I have to understand better what's driving outcomes. So that's from a economic or research point of view. There's also a very, very different view, and that is if you work on anything housing related, you're operating in a tightly regulated environment, at least in the United States and parts of Europe, and I also think in the UK. So any system that is helping to create recommendations for mortgage applications, or that is screening tenants, or that is really having influence on the housing outcomes of households, then by law, we must not discriminate in terms of gender, race, ethnicity, disabilities, and so on. So there's a long list of protected attributes. And we simply, if we discriminate on that, if our system discriminates on that, we're breaking the law. And it's not only illegal, it's also unethical. So that's something we really do not want to do. So whenever we are developing machine learning enabled systems that are operating in these environments, then we should really be sure that the system is doing exactly what we think it's doing, and it's not cutting any corners, and it's not discriminating against people. So there's a number of reasons why it's desirable to understand better what's happening inside the black box. Let me give you a quick horror show of examples where this has gone wrong in the past. So Amazon tried to create an AI-enabled recruiting tool, which turned out to be sexist in the end. So it was discriminating against women. And you know, if a tech giant gets it wrong, what are the chances that we might be creating something like that in our own little systems? And Amazon did it not only once, but twice. So they created a face recognition service that was discriminating against people of color, and especially women of color. And that thing had to be taken down relatively quickly just because of that inherent bias. And that came out of the training data, came out of the models, and it was something they couldn't simply quickly fix. The system was, in a sense, broken at the core. So that's Amazon twice. We also have Microsoft, who tried to train a chatbot using Twitter data. And you know, what could possibly go wrong if you feed a lot of Twitter communication into an AI chatbox? Well, within a day, that chatbox became racist. So it was communicating with people and things that you do not want to see in a chat box, and Microsoft had to shut it down after a day or two. So this is then examples of big tech companies getting it wrong, but in that sense, it wasn't really a big problem. Well, it was a big problem, but they just had to turn it off, and that's it. There's a new development now at least in Europe, that makes companies liable if their machine learning enabled systems are discriminating against some groups. So this is not just in the housing sector. So here's a case from Deliveroo that is using a machine learning system to allocate delivery tasks to its riders. And that system was discriminating against specific groups. And the novel thing about that court case that came in at the end of 2020 was that a company is liable if the system is going rogue. And that is new, and that is then given even more importance to the kind of analysis that we're trying to do here in our research. So the core message, the positioning here is that predictive power itself is not good enough. We need transparency. We need to be able to conduct due diligence. And in order to do so, what we try to do is we try to copy a best practice approach from software engineering that is called system testing. And that just means that whenever you create a system, you directly think about ways how you can test that this system is operating in exactly the same way as you want it to be to perform. So there's two steps. You set up the code to run the system, and then you directly set up a number of automated tests that serve as a check in the background. So whenever you change something in the code, you can run the checks again, and you know again that you can be certain that your system is performing exactly the way you want it to. And that's what we do. And we can do this, and we should do this, because training a machine learning system is nothing but software development. So we should then follow the best practices and define and implement a system test when we train models. We believe that these tests should be independent of the training process. Parts of these tests could be already part of the training process, but then there should always be a second distinct step or layer that is checking that these the overall goal of that system is not compromised. And what we found in our research is that we really have to create these tests for each model for each task new, because each task will have individual task-specific needs, and we can't just copy system tests from one task to the other. And in our paper, we give two examples that then show how such a system test can be implemented. So we go back then to the vintage classification example that I started this talk with. So what we really want to know is, okay, which aspects within the picture really lead to a specific classification? And architects told us that they would focus on the windows, they would focus on the doors, roof lines, maybe the ratios, brickwork, bonding of bricks, and so on. So for us then, we thought, okay, this would be a great way to test our model, was to say, okay, if our model is looking at exactly the same things that a human expert is looking at, then we're relatively confident that it's picking up the right cues. If it starts to focus too much on backgrounds, clouds, the street, cars, people, then it's not really about the building at hand, the task at hand, but then it's just trying to get cues from other things that are visible on these images. So that's the first idea of our system test here, to just see, okay, can we describe what really matters for these classifications, and does this then coincide with the human expert input? Of course, this test should be automated, and it has to be able to run on a large sample very quickly. So it should be not, let's say, human driven. Okay, in this very simple example, what we do is we first try to see what is really on these pictures. So we use an off-the-shelf object detection model that can show us where buildings are, where trees are, where cars are, where doors are, where windows are. So all these elements that the architects told us should matter. So using these already trained models, we can directly identify those objects that we hope that our machine learning model is also picking up. In a second step, we use something called local interpretable model agnostic explanation algorithm, or simply LIME, that figures out which pixels in an image were really the most relevant for a specific classification. So these pixels are called superpixels. And so in this example that you can see here, this house has been correctly classified as being from the interwar period. And then using this LIME algorithm, we then can see that this classification was mostly based on that ground floor bay window, a little bit of brickwork, and a little bit of the proportions to other windows. So, but it's important to understand that LIME does not really know what's going on in these images. LIME only says these pixels matter. And what we now do is we just bring together the object detection from the previous step with these superpixel detections from the LIME, and then we just see whether there's an overlap between the two. And if LIME is nicely picking up doors and windows, then we know that our model is behaving like the architects say it should be behaving. So that's the entire test here. Just to give you an example on models that sometimes get it wrong. So here we have two examples of exactly the same house, and where where the image has been classified as post-war building on the left-hand side, and there the superpixels are all in the sky. So they're not about the house itself, so it's picking up something, and this is something that we don't like to see. So this is not a good signal, and the same on the right-hand side for the Edwardian classification. We see that it's mostly about the threshold of the door and a lot of fence. So this is, again, not optimal. And these are just examples on good superpixels and in our system test thinking bad superpixels. If we then run this comparison of superpixels versus detected objects on all images in our sample, then what we see is that, relatively speaking, windows matter, doors matter, and trees don't matter. And I can see that by looking at these scores. Whenever the score is higher than 1, then this means that there's an overrepresentation of these objects in the superpixels. If it's lower than 1, there's an underrepresentation. So having a score of 1.336 for Windows, that is good. It means that the model is really picking up the windows correctly. If you look now at this table, there's one thing that should not be so comforting here, and that is the score of 1.167 on cars, meaning that our model is actually looking a little bit too much for my taste on cars. It should be below 1 because we're talking here about building styles, and we're not talking about cars. But doing this system testing approach here, we finally know that there might be an issue there with cars in our window and cars in our images. Okay, so this was for all buildings in our sample. Here's the same logic, but then for different vintages. So for buildings that have been classified as either Georgian, Victorian, late Victorian, Edwardian, interwar, and so on. And overall, the pattern is very consistent. So there's always a good emphasis on things that should matter, windows, doors. And there's not so much emphasis on trees, which is good. But if you then really look at the last row again, the second column is a bit an outlier, because we see that for buildings that have been classified as Georgian, our model has been looking way too much at cars. And so we're now aware that there might be an issue here with our model, that we might need to revisit our training data for Georgian houses. So by doing this exercise, we simply know that, that overall we get a good identification, but there are these pockets where we should probably pay a bit more attention and improve the training data and the model. So we're now certain where the strengths are, and we know where the weaknesses of our approach are. And yes, having this focus on the characteristics that the architects said, that is a good thing. So when houses have been classified correctly, then we see that there's more of a focus on windows, doors, and less of trees, compared to cases where the properties have been classified incorrectly. And these differences, they are statistically significant. So yes, it really helps to focus on these elements, which is again reassuring. Okay, that's test number 1. In test number 2, we work exactly with the same data. We use exactly the same tools, but we ask a slightly different question. So what we try to do here is we try to see whether we can learn something about the value of these buildings from the images. And the idea is that we might, from the outside, have additional information that might, give us cues about a house being particularly expensive, well done, above the surrounding buildings. And just have a look at this example here from a street close to my house, where you have 2 semi-detached houses, and one of them has a Bugatti and a big Mercedes-Benz in front of the house. And just by, let's say, analyzing them, then these visual cues, we might hypothesize that then if you have a Bugatti on the driveway, you also might have a more luxurious kitchen in the inside of the house. So this might be a cue on the value of the house. And we try to exploit then these kind of extra information in the images. So just for just to have something to play with, we build a very, very basic automatic valuation model that is then incorporating image data. So we first run a hedonic model. We take the error terms from the hedonic model, then we train the classification into value quintiles of these error terms from the first step. Then we use the machine learning classifications of these error terms into quintiles. We use that then as additional information in the second step, where we then rerun the hedonic model, including these information residuals. And of course, we do this out of samples, so there is no information slipping through the wrong way. And we run two versions of that model, one that is incorporating already the vintage information from the previous step, and then another model that is simply not incorporating that information. So we have then, the idea here is that if you already have vintage information in your hedonics explicitly as a variable, then these information should matter less in the images. So we would expect that then our classification model is not really picking up that many cues that are really about vintage, but about other things. So plainly speaking, we don't think that doors and windows should matter that much anymore, because we already have them in our direct control variables, but it should be more about the cars in front of the house, for instance. Okay, so that's the idea. We see that we can increase the predictive power of our AVM by including image data. So the root mean squared error is going down, and the mean average error is also going down if we include image information and classify residuals into quintiles. So that is nice, it works. It's really, the numbers look small, but if you go from 22% to 20%, that's at least a 10% improvement in model fit. So we're quite happy about that improvement in our ability to predict values. So what we now have is a table that is very, very similar to the table before. Again, a score of 1 means that a model is not over or under emphasizing a certain characteristics of these images. And what we see is that in the model where we do not control for vintage through the hedonics, so where all that information is still picked up by the classification of the images and the errors in the error term modeling. In those cases, there's again a huge focus on windows and doors. So there's a 1.3, 1.4 score in column 1. In cases where we already control for the vintage through the hedonics, through a separate step of analysis, in those cases, the score for windows and doors is going down to basically 1 for windows and 1.1 for doors. So there's less information then that can be derived on top of the classification we already have out of these windows. And this is exactly what we would expect. Then again, going down to the last row, the score on cars is not changing. And that is also interesting, because that means that including information on the vintage directly through a control variable does not reduce the relevance of the car information. And first of all, the car score is higher than before, so we're now at 1.6 instead of 1.2, and it does not change depending on the controls. So this is then confirming our hypothesis that when we create models that value properties, then information such as anything that is related to vintage is still relevant, as long as it's not already controlled for through the hedonics, and additional information such as cars do matter. So cars help us to price houses. So that Bugatti, that Benz, they are meaningful when looking at values. They're not that meaningful when looking at vintages. So what did we learn from this exercise? We have now a better understanding of the inner workings of the machine learning black boxes. It is far from perfect, but we could see that models behave similarly to what human experts would suggest. And these findings are really helpful for improving the classifications, because we could then for another training set, we could really focus on then windows and doors. We must make sure that they are visible. We should avoid trees, of course, and so on. So we then know how to really take these pictures in a meaningful way to improve the model fit. Also, we spotted problematic combinations. So if we're investigating Georgian houses, then we should really make sure that we do not have images that have too many cars in them. So the main takeaway is that all this information about how these models work, we would not have it if we hadn't done this system testing stage, this explicit models are picking up. So we think that this is absolutely essential if you are operating in a regulated environment, because now we could at least say, you know what, our vintage model is not picking up cars. If you then translate this to something that is more meaningful, if you say we're now analyzing a system that is allocating mortgages to households, then the question would obviously be, okay, does this system discriminate against women? Does it discriminate against minorities? And if you then define exactly a test that will look for any discrimination in the outcomes, well, then you know that you can tell the regulator whether your model is clean or not. So that's the logic of that research. Right, what are we doing next? So this is something I'm really excited about. That's a new project that I'm currently doing with my great colleagues Colin Schmidt and Wayne Wen. And what we try to figure out is what it is that people pay attention to when they're looking at houses. So we built a little app that lets people like and dislike photos of houses very, very easily. So it's just swiping left and right, and you can do a lot of these classifications within minutes. And then what we then do is we train a machine learning model based on these personal tastes. So we create a sort of a digital twin. I know it's a buzzword, it's terrible, but this is actually what we do. So we create something like a machine learning enabled system that is able to anticipate your decisions on like or not like of buildings. And that is interesting because then we can apply the same LIME techniques that we applied before. We could really see what it is that, for instance, I like about buildings. And that could be things that I know already. So I know that I like a bit of space around the house. I know that. But there might be things that I'm not aware of. So I might have this hidden taste for, I don't know, greenery or specific window ratio or things like that I'm not really able to communicate, but that will still lead my classification of a building into something I like and something I don't like. So by having then this digital twin, we can really then identify both the things that you know you like and also the things that you might not be aware of. And that is really, really exciting. Also, we can then test whether people have very different tastes. So is there a homogeneous taste for specific characteristics, or is this really dependent on demographics? Is it dependent on person-specific experiences or just genetics? There's a lot to be tested there, and I'm really, really looking forward to that, because one thing that I'm always surprised by is this one size fits all, lowest denominator kind of design approach that can be seen in quite a few large-scale housing developments on this island here. Okay, so once we can then identify attractive features, once we can then say, okay, what it is that people look at, what it is that they like, we can also do one last step of analysis here, and we could see whether the revealed preferences that the models are telling us about the preferences of people really fit than the preferences that people self-report. So I just said, I like green space, but maybe my model says, well, actually you don't. You care more about, let's say, the size of the building or something like that. So these possible contradictions or confirmations are really something exciting to research, in my view. I very much invite you to take part in this experiment, in this survey. So there's a link down there on the slide, fourwalls.kreml.com. Hit it up with your mobile phone, and then you can swipe a few images for us, and then we can create a digital twin for you. It's fully anonymized, so nobody will know about your preferences. All right, so that's from my end. So these were then the type of things that we're working on at the Department of Land Economy in Cambridge. And I'm very excited to hear from you, and either now in the Q&A or through email or on Twitter. That's my story. Thank you very much.
Yeah, thank you, Thies. It's very cutting edge work. I cannot pretend that I understand everything, but I have a question because I think it's a very open one, but because when I look at this work, I feel like it's very UK centered, because you look at the outside of the houses and determine whether it's Victorian or Edwardian. So I know it's mostly a method focused work, but how do you feel it can be generalized to other countries, this method?
You're absolutely right. So it's not only UK centered, it's Cambridge centered. So most of the sample is just from this small town here. And classification into vintages is meaningful in the UK setting, yes, because vintage means so much about the quality of the buildings, the design of the buildings, the location of the building. So it's a really, really powerful variable. So it's worth investigating, and we don't have the kind of information in the land registry data. So I'm not making excuses for analyzing that, but then at the same time, this method could be applied for so many different characteristics. So yeah, it could be upkeep, it could be the size, it could be in the United States, people have used street level images, not housing level images, but street level images to, for instance, do a census. So they then roughly know what type of people live in what type of streets. So those letters that we get, you could maybe do without them if you then analyze the exteriors of buildings and then link it to, for instance, demographic variables. So it doesn't have to be vintage. But then again, you have to start somewhere, and vintage was easy. And I saw a preschool class of kids walking with a teacher through the street, and the teacher would explain to them, this is late Victorian, this is Victorian. And I thought, okay, this is a nice thing to investigate. If kids can do that, then a computer may be able to do that as well.
Right. So if you apply it to other countries or in other characteristics, do you need to train the model again?
Yes. So of course, you have to train it every time again on. So even if I wanted to do this again in the UK and I wanted to look at solar panels, I would have to train the model again. But the good thing is that these training, this classification training steps, they are not that computing intensive, because what we are working with, or what we've worked with, is a transfer learning approach. So training a model on Cambridge and all houses, that took 20 minutes, half an hour on my laptop. So it's something that is absolutely in reach. So you don't need supercomputers to do that. In other countries, you might not be able to use Google Street View. Germany doesn't have it, at least no recent ones. So there you could use satellite images or other multidimensional data. So it doesn't have to be street level images, but they work well.
Okay, great. So I'll start take questions. You can still type in the Q&A box. When you ask questions, if you can mention your name and the affiliation, that would be great. So we'll take the first question from Michael Hodge. Michael, if you can unmute yourself. Thank you.
Hi there, can you hear me?
Yes, hi Michael.
Hi there, hi. I'm just wondering, it's more of a kind of data access kind of question. So I work at the Office for National Statistics. We've did something similar in the past about kind of greenery on streets. Where we fell over on trying to upscale it was that we ran into the problem of Google not allowing access to the data, because via their terms and conditions, you should only store it in memory. You shouldn't store it, you know, permanently. So how did you get around this?
We stored it.
Okay.
What we did though, and that's important, we stored the feature vectors. And we can store the feature vectors. So the moment we get it out of Google, we directly run it through that computer vision step. Then we don't need the image anymore, because we only work with is the feature vector. And so I think that would be a way around the problem there.
Right, okay.
Could be a way around the problem. But then again, if you want to redo it then with an updated computer vision model, so the first step, then you would need the images again.
Yeah.
For us, what we are sharing with other people is never the images, because we don't keep them. What we share, and you know, to reproduce our work, that would be the feature vectors.
Yeah, sure, that's fine. I just had I'm actually in the car at the moment, so I had to pick up someone. So I've forgotten my I had another question there. Would the host kindly remind me what my question was? Sorry.
You mentioned about Amazon and Microsoft examples. And,
oh yeah.
Yeah.
Thank you. So yeah, it was really nice to hear the Amazon and Microsoft examples, because they're fantastic examples where things have gone wrong and it wasn't really considered the kind of ethics and the kind of discrimination those machine learning models can kind of give. I think one of the outcomes from that was this need to engage with the community about these models. Is this something you did here? Did you kind of have any outward engagement, or just anything along those lines, really?
No, not really. So what we talked to a lot with architects and estate agents. So we try to understand what it is that really, you know, determines vintage. So we try to use expert information, but then we did not, you know, have any further engagement with community. No, we didn't.
Yeah. Okay. Thank you. Yeah. It's I guess with those Microsoft and Amazon examples, you know, they have far-reaching kind of societal effects. But this was a really interesting talk. I'd like to kind of chat to you a bit more in the future. So I'll reach out via email. But thank you very much.
Thank you.
Thank you.
And next, Tony Cox.
Hi, Tony.
Tony, could you unmute yourself?
Oh, sorry about that. Sorry, I thought I had. Right, yeah, you talked, I think you've partly addressed my question in your talk, but the algorithm you've developed, you were stressing you need to rule out things like trees and background. But I'm interested, if you're trying to place a value on properties at the end of the day, then trees and background might be very important. I mean, background, for example, if you're living next to or your house is next to a fast food outlet, for example, you'd expect that to have an impact on value. It's one example. And other things that are hidden, like the square footage of the property, and indeed solar panels that might be on the rear roof that's not observable from the street. So I just wonder how you take account of things like that. And if I may, I had another question, a separate question. When you've produced the vectors, can you check on the quality of the vectors? i.e., can you take the output from the vectors and reconstitute the property itself presumably in a schematic form, just to check it does indeed look like the original picture that you had?
Okay, great questions, both of them. And you're absolutely right. So depending on the task, you might want to have a look at the background. So if it's about value, then trees might be meaningful, cars might be meaningful, and the surrounding also might be meaningful. So I'm 100% with you there. And so therefore, I'm really pleased, for instance, to see that cars have a higher loading in the analysis when we run an automatic valuation model, and less so in the first step where we just want to know about the vintage of the house. For the vintage, in the paper, there's a detail which I didn't talk about, but which is something I'm very proud of, is we also look somehow at the neighborhood, because there's a spatial correlation in the vintages. So we get better results if we also look at the neighboring buildings and then see, okay, if they're all Victorian, then the odds are pretty high that yours is also Victorian. So that's just a technical thing, but the logic is simple. It's more that, okay, if we just want to really see how this house looks like, then we should ignore the hedge and the trees. If we want to talk about value, they matter. So I'm there with you, and so that's we're on the same page. But I would like to know whether the model is picking these things up or not. Right. That's one thing. The other thing you're talking about is going into the direction of GANs, so adversarial networks. So where you then first encode an image into something like a feature vector, but it's more than those 2,000 elements. So these are really, really larger representations. And then you go from there and try to recreate these houses. And this is nothing we can do with those feature vectors here, because this is a very, very different type of models. And those feature vectors, we try to make sense of them. We can't. So it's not that the first, 3 elements is about the roof line, and then there's something about the windows and so on. It's not like that. So what you then need is pattern recognition on these feature vectors. So therefore you need the second step of machine learning that is then leading to these classifications. And that works pretty reliable. And it's surprisingly few images needed to really create such a model. So this is powerful, it works well, but there's no clear link there. What we've done in a different project, which is just a fun project, is we try to create fake Victorian houses. So we fed all our Victorian terrace houses into such a GAN, and so in the end we created some slightly distorted houses that don't exist. They look like Victorians, sometimes they're missing a door or something like that, but it is actually possible then to recreate images from these feature vectors, sort of. And yes, if you swipe enough images in our app, we could then create your dream house if you wanted to.
Thanks very much.
And then we have a question from Alex Holmes. Alex, if you can unmute yourself and ask the question.
Oh, I think I might have accessed it. Sorry, I'm not Alex Holmes, but I've got to use his link to join. I'm really sorry, but I think the question came from me. So yeah, thanks a lot for the presentation. I just wanted to ask, So, in the classification algorithm, sort of you mentioned, trees and cars are problematic, but actually, you also have a package that identifies them. So my question is, why, wouldn't a simple solution just be, strip these things out of the images, or just focus on, things like windows and doors before you run the classifications? Because, that way, that it is really mapping to what a human expert would be looking for.
That would have been a different approach. That's correct, yes. But then again, is that step necessary? If what you could do is you could then compare the predictive power of the model where you don't do that, and where you train your classifier on images where you've cut out all the trees and so on, and then see whether you get different outcomes from that. But so yes, this would be an approach, but what we really would like to do is we would really like to be able to say, by the way, trees don't matter, or trees do matter. So having this clear statement, or this clear identification that we should pay more attention to specific objects here. And if we run a system testing second stage, then we can actually say that this matters before we adjust basing. We are just using the architect's views and then just cut out trees, and we don't even know whether we need it or not. So I think the decision to then, for instance, crop trees out of the images would then be a third step after first classifying, then doing the system testing, then seeing, okay, trees are not improving the quality of the classification, so let's take them out. So I think there should be such a sequence there, so that we then really know what we're doing. But yeah, one could also do a trial and error and cut out specific objects. That would have been another way of analyzing that. That's true.
Thanks. Yeah, it just seems interesting because some of the, I think you were showing, like for like Edwardian, for example, it was just sort of plainly wrong. I mean, where the super pixels were. I just wonder if if you sort of cut out things that you knew were irrelevant, from the outset, what difference it would make, or but yeah, thanks a lot.
What we are really surprised about is how robust our classifiers are when it comes to all the stuff that's around houses. Trash cans, all the stuff that people have around their houses. It doesn't matter much. So the models are really good at picking up the important bits. So yeah, that is something we found really encouraging. Also, given the quality of the images we get out of Google Street View, which is not the best. It's low resolution. If we had better images, I think we would get accuracies in predicting easy tasks such as vintage, which are almost perfect. Right now, we don't have perfect classification, but we could get there, I think.
Thanks.
And we have a couple of questions from Benjamin Fraser.
Hi, Benjamin.
Oh, hello there. Thank you very much for your presentation. Super interesting. Just a few questions, if that's all right. So first of all, you mentioned digital twins, and you alluded to the user preferences that you'd use for that. Do you think in the future we'll make use of a lot more composite digital twin models, so using tabular data, image data, along with those other preferences that you stated? And how impactful do you think they'll be?
I have to be careful here because I'm pretty cynical about quite a few of these twins, because many times when people talk about twins, they talk about copies. And I think a copy is something different from a twin, because a twin has its own, it's not just replicating what the other person is doing. So what we're creating here is something that is very, very similar to the participants, and in this very specific, I like it, I don't like it classification task. And having such a twin could be powerful, for instance, when it comes to pre-screening listings that you might want to look at when you're looking for a new place to stay. It could help you to improve your preferences when it comes to your surroundings. So you could, for instance, planning processes could be easier because if everybody had a digital twin on tastes, then we could simply say, okay, this design is best liked by everybody within 500 meters. But then again, this is what we are figuring out right now. What we are figuring out right now, the hard way, is that you need quite a few images to be able to create a reliable digital twin. So this is nothing that an estate agent can quickly do before they show you the listings. So we're trying to figure out, okay, how much input do we really need to get something reliable here? So we're at the beginning of that, and we hope it will be useful in the end, but not making any promises here.
Yeah, absolutely. Thank you very much. So a second question, if that's all right as well. So I think you almost answered it earlier, actually, and it was about confounding factors. So for instance, location, it wouldn't generalize to other areas. Do you think perhaps extra methods in addition to just data-driven methods, so like causal modeling and things, could help in this regard?
Yes. So there are different ways how you could then combine causal modeling and machine learning techniques. One would be just to, let's say, use the machine learning models just to derive additional variables, and then do the causal modeling in good old school econometrics. And maybe, I don't know, this is what we did in our first paper. So we just got additional information out of Google Street View and then threw this into a spatial model, and that's what then in the end the findings were about. Establishing causality in machine learning models remains a challenge, and that's something we're really interested in. We want to work on that, but it's nowhere near the already difficult causal inference that we see with traditional econometrics. So it wouldn't be my first port of call.
Absolutely, yeah. Thank you very much. Yeah, obviously we're still very immature in that regard, but I think it's important for the future nevertheless. So a final question, apologies for lots of questions here, but so you mentioned your object detection model, which you used. I didn't recollect whether you mentioned whether you had labels for those. Did you manually label a subset using bounding boxes, for instance, and assess the performance of the off-the-shelf detection model that you used, or did you not worry about that?
A colleague of mine did that, actually. So that's Mike Langen, and he's out in Reading now. And part of his PhD was on exactly that, so trying to see whether it's worth it or not. And so to retrain the object detection yourself. And the take that what I understand from his research is that it makes sense if you wanted to look for, I don't know, electric chargers for cars, because they are not in the pre-trained models in there. But if you're interested in something as basic as a door or a window, the pre-trained stuff is pretty perfect. So it doesn't really make sense. It doesn't really improve accuracy a lot if you train them your own object detection model on these basic characteristics.
No, yeah, I suppose it's only if you want to generalize to something more specific in that regard. Yeah.
Yeah, if it's I don't know, garbage in the front lawn, if it's satellite dishes, if it's stuff like that, that is very housing specific and not part of this set of, I think, 2,000 or so labels that the standard models can deal with. Well, then this is something you might want to look into. Also, if you wanted to combine characteristics, so if you want to detect, I don't know, a Victorian house, not just a house, then you would have to train yourself.
Brilliant. Thank you very much.
And we'll, at last, we'll take some questions from David Bolat.
Thanks very much. Superb presentation, Professor. Just a couple of questions, one logistical and one a little bit more speculative. The logistical question is, how did you source the data for the target variable, that's to say the house price information? And the more speculative question is, how do you think a model like this could be adapted for other use cases, for example, by banks to model default risk?
Great questions. So we got the left-hand side prices that came from the land registry house price data, or the classifications and styles, they came from a huge sample of manually classified images that our friends at the architecture department did for us. So they were going through a few, I think 25,000 images, and said, okay, this is Victorian, this is Georgian, this is, we have this large ground truth data set. So you need those to be able then to do these training, being able to train these models. So yeah, that's the challenge, to have both the left-hand side and the right-hand side. Your second question on, let's say, modeling mortgage default risk, that is something that I'm personally interested in from a real option point of view. So in the past, I've done research on how real options make buildings more or less risky as an investment. So if you have an option, if you have a building that can be expanded much, or then this will appreciate more in price and then boom, and it will fall more in price in a bust. And so everything else equal, if a house has a lot of optionality in it, it will be more risky, and that might be important for a lender. And one new project that Wayne Wen is working on here in Cambridge is trying to use these type of models to detect optionality in buildings. So if Wayne gets his trainings set up correctly, then he will be able to say, okay, this house has a lot of potential to expand, for instance, and therefore it will be more risky. And that might be then important for a lender to assess then the asset-specific risk, and yeah, maybe then use that to price that mortgage accordingly. But then again, if the lender really does that, they need to be sure that they're not cutting any corners anywhere. So then they need then the system testing approach as well.
Fascinating. Thanks very much.
Thank you. I think I can ask a quick question from Ian Grimstead from Office for National Statistics. He's interested whether this Lime paper has been published or not. He's interested to read more details about this.
Yeah, it's published. It's not only published, it's very, very highly cited. It's very impactful. It's a fantastic paper. I love it. It's by Ribeiro and others. And if you look for, send me an email, I'm going to send it.
Okay. Yeah, that's great. Thank you, Thies, for this very interesting talk. I can see the conversation is heated, so there are a lot of interest. If you have more questions, just drop Thies an email. I think he can be very happy to answer. And for the interest of time, I have to end this seminar. Let me remind you that the next webinar will be on the 25th of March. We will have James Michel from the Federal Reserve Bank of Cleveland. He will present his work on censoring of the Bank of England's density forecasts. This will be the last of this webinar series, and we welcome everyone to attend. Thank you for your time and enjoy the rest of your day. Thank you.
Thank you very much.
Bye.